Welcome everyone to Altair Consumer Electronics webinar series. Thanks a lot for joining us today. I'm Sundar Gopalan. I'm currently leading our marketing team here. Just a little housekeeping before we get started. If you have any questions during the presentation, please feel free to type in under the question box and we will address through the course of this webinar. The objective of this webinar series was to mainly focus on two key tracks. So track one focuses on mechanical series, where we will cover end-to-end solution from ideation to execution, going through some of the most complex structural and manufacturing challenges by using real-world examples. We will also demonstrate how Altair's multiphysics platform offers the most comprehensive solution for the simulation and optimization problems currently in the market. And our second track is actually focused on electromagnetics. So this will leverage our electromagnetic platform, where we will discuss a wide range of electromagnetic challenges associated with consumer electronics product design that ranges from a PCB design and verification up to manufacturability. As we live in a smart world with numerous interconnected devices, our presenters will use real-world examples that covers the antenna and PCB design, its placement and optimization process, as well as evaluate potential coexistence and interference challenges between these interconnected products. During the course of this webinar series, we will demonstrate these solutions using various electronic devices such as smart speakers, hand controllers, and a Bluetooth mouse. Why Altair? So Altair is pretty well known in the market, serving different industry verticals, where we can actually provide end-to-end solution that starts with the designer on the ideation phase to a CAE analyst that can solve some multiphysics capabilities, and it goes all the way up to the manufacturability and even digital twin, where we can leverage our data analytics solution and our IoT platform to build a digital replica of a model and compare the results. We also leverage our high-performance cloud computing solutions, where customers can actually run a lot of these jobs at a scale and at a really quick period. Finally, Altair also has a unique licensing platform where you can access third-party applications using our existing license. So how exactly are we serving the consumer electronics market? Our multiphysics platform provides end-to-end solution where we can solve problems at different stages of your product life cycle. We can begin at the component level, focusing on the structural integrity, PCB and antenna design. We can go at the assembly level, where we focus on the interaction between multiple parts, where we can evaluate electromagnetic compatibility, thermal behavior, vibration, and even the acoustic performance of that product. And finally, at the system level, you can build a digital twin of your physical asset and optimize the entire product performance. So we leverage our optimization solution at every single stage, and we can also leverage our high-performance computing and cloud computing capabilities at every single stage of the product lifecycle. So what's our value proposition to the market? So time to market is one of the biggest challenges in the consumer electronics industry, and Altair's multiphysics simulation and optimization workflow has helped customers reduce physical testing costs and streamline their simulation iterations, even leveraging our machine learning algorithms. So customers can solve a wide range of applications and achieve this efficiency gain using a single flexible simulation platform utilizing a single license. So that's the key takeaway from today's webinar, or this entire webinar series, that you can pretty much perform anything that we show today to you using a single platform and a single license. You don't need to add additional modules that we would present today. Earlier this month, we reviewed how simulation-driven design can save time and money using our multiphysics modeling process. This webinar, along with other webinars, are actually available on demand, and I would highly encourage the attendees to review them if you have not had a chance. But for today's webinar, we're going to take it to the next stage. Now, we looked at the different modeling practices, and we will review today some advanced automated workflows using real-world examples with a specific focus on the noise and vibration use cases, as well as how do we improve the perceived quality. Our presenter today is Ismail Benayoun. He's our technical director, and he has over 12 years of industry experience where he has worked with several consumer electronic customers, not only in the Europe market, but also in the West Coast market. So he brings in a lot of experience in this domain, and Ismail will be presenting our multiphysics platform today. Ismail, the floor is all yours.
Thank you, Sundar. So let me switch here and please let me know.
I will make you the presenter in a second.
Perfect. I hope you can hear me clearly.
Yes.
Brilliant. And
so
let me.
Screens, that's all yours.
You can see my full presentation mode, I hope.
Yes.
Excellent. Thank you again for the introduction. Thank you to everyone being with us here. I can see that some of you guys have been following us already during the complete series. So today is basically the multiphysics topic part 2, if I would say so. And I would jump into the topic right away. So we are actually focusing on the electronic devices and products. And obviously, as we all know, they have certain trends and challenges. We all see this trend of miniaturization. Things are getting smaller and smaller. Computers are becoming tablets. Tablets are becoming phones. And at the same time, performance and expectation on performance is continuously increasing. At the same time, we see that there is a huge competition. Sundar mentioned about the time to market importance and how many products needs to come out there, and the challenge on the cost and the cost reduction. So every manufacturer out there is trying to reduce that aspect. More you think about it, more you see that all these trends are driven by customer expectations. We are people in the industry, but we are the customers at the same time. And what is hidden behind these customer expectations? It's a big part of it is perceived quality. So here is already a big question mark. What is perceived quality? It could be defined and expressed in many different ways. One word that summarizes perceived quality is subjectivity, right? I've put an explanation here, or a definition of perceived quality, which you see that is defined as the customer perception of the overall quality or superiority of a product or service with respect to its intended purpose relative to alternatives. In other words, it's actually the perception aspect. So to tackle and deep dive in this particular topic, I picked one of the examples here in a speaker assembly, a smart speaker assembly. And you will see the reason why we took that, because it's one of these complex systems. They come in all different shapes, in all different sizes. They are integrated in those smart devices nowadays, from a watch to phones to smart speakers. And when you look in the industry, the notion of perceived quality is still driven by physical testing. Checking for perceived quality is still very much a physical testing task. So a legitimate question is, are there any alternatives? Well, the short answer is yes. Simulation-driven process is an alternative and is becoming more and more an alternative to either reduce physical testing or even eliminate part of it. And most importantly, it's bringing and improving the decision-making during the product development cycle. And this is what I want to emphasize today, on how simulation can help you bring these things in your daily work. So let's look at the model we would be discussing around. So what you see here is a model that is put together by the Altair team. We have been working around the different products and parts in this assembly, everything from the loudspeakers to the PCB assembly to a fan to the heat exchangers. And if you look at this assembly, for example, And we're going to pick a couple of challenges and requirements here and see how we can solve them together. So one of them is actually looking at the fatigue and function losses due to vibrations and due to operating mode of this assembly. We could also look at sound pressure levels, basically the sound quality. How does it match certain targets? How does the speaker assembly performs in different environments? And a final aspect here, and this is where we start touching to the perceived quality, is are there any buzz, rub, squeak, or rattle? Don't worry, if you're not familiar with these terms, I will define them more in detail later in this presentation. But if we were to look at these four main requirements, one essential aspect is actually the load definition. We need to know, first of all, what are the loads to be considered. So these are, you can see this as the agenda of this presentation today. So let's zoom out for a second and look at the product development cycle. Typically, and I would say always, it starts with an idea, with a concept, and it goes through the steps of developing a design and maturing a certain design of components and system and putting all these systems together. It is essential to know and remember that these complex products requires multiple attributes to be checked, everything from different physics, electromagnetism, vibration, thermal analysis. We will be looking through this complex matrix of validation. This is the topic of today. Now, in order to solve all these physics, it's very important to have a simulation process that allows to analyze all these aspects during a reasonable time. In the previous presentation, and Sundar mentioned that earlier, my colleague went through in a lot of details about how this simulation process could look like or typically looks like. So for example, to set up a CFD analysis, thermal stress, nonlinear analysis, and vibroacoustic, you typically see in the industry multiple engineers working on multiple models, multiple interfaces, and spending, let's say, roughly 10 man-hours per design iteration. Why Altair? What are we proposing? We are proposing a radical change in this scope. We propose a process which is quite unique and is based on what we call the single model multi-attribute. This is about one single platform to execute and to analyze all this physics. And it's about reducing up to 70% your time spent on simulation and analysis. I highly recommend to watch this webinar where Ujwal is going through these very interesting topics in much details. So back to today's topic, where we will deep dive in certain specific cases. Step number one, what are the loads to consider for designing the speaker? Well, if we take a vehicle, we all know, we all have a car, we've all been in a car, let's say. A very important aspect in designing a vehicle is the load definition. Is this road loads excitation? They will define how all these parts need to look, how stiff they need to be, and how comfortable a car will be and how durable a car will be. Well, for the electronics devices and products, it's not different. It's not different for a speaker neither. And in this case, we're talking about the speaker membrane excitation. We can definitely wait for physical parts to be physically tested, or we can apply simulation. Well, it's about applying simulation. And this is what you can do in Altair's low frequency EM simulation platform. We have the capability to model these voice coils, magnets, and plates and simulate these systems. We have the possibility to define this parametric model, so it is very easy to adapt to the size of your products and to the versatility of the products you might have. In this platform, we have embedded material libraries, which is also fully customizable. So it means that you can bring your own knowledge into it. Very important in a voice coil simulation is actually the type of currents you want to do or you want to use. They could be driven by a formula, basically a sine sweep or anything like that, or they could be driven by a very specific load. So when you think about it, is actually if I want to see how my membrane vibrates for a specific song or for a specific track that I use to design my parts. So what's happening in this process is obviously the electromagnetic simulation calculation and flux calculations. But what we can get from the same simulation is actually the position of the coil and how the position varies versus time or versus frequency. Well, this is nothing else than the loads that are required for our simulation. The way the voice coil vibrates or moves is the way the membrane vibrates. And these are the loads that we can take into our vibration and finite element simulation. And here you see, for example, a component analysis. This is the speaker itself analysis, and you see how the enforced displacement will result in the vibration of the complete system. So now we have the loads, and we can bring these loads into the system and apply the system to the rest of the assembly. So very importantly, we have a well-defined workflow, a well-defined capability to do this type of analysis, and in some sense define the loads because they are very important. So now that these loads are ready, we can move on with the other attributes because we have the prerequisites. So we will dive in now into the vibration, the different type of vibration analysis. It goes without presenting. Everyone starts with normal mode analysis. This is the basic requirements. And when we have this model in place, we will start looking at certain specific. One challenge or one element we defined from the beginning here is actually to look at the induced fatigue due to vibration. And we take the example of a PCB. Let's say that we have a criteria here that within a frequency range from 5 to 1000 hertz, the maximum acceleration that the PCB should withstand in all directions is 50 Gs. Well, the analysis process that we will follow is taking in this finite element model, applying the different excitations at both speakers, and investigating these different vibration levels, going through the complete process of diagnosis and optimization when required. So let's look at this in detail together. Applying the vibration profiles, in this case, we are working in the frequency range. We are focusing on the 1000 hertz range because this is where we have the highest amplitudes that are working. In this analysis, there is no limitation on how many outputs we need. We could be tracking any system or any part in the assembly. For this particular example, we are focusing on the PCB, and we want to track this acceleration as I mentioned earlier. As part of this workflow, which is highly automated, we can track this particular, let's say, accelerometer location and see how does the acceleration levels compare to the target. And we can see automatically that we are violating a certain target in the Y direction. So from here, we can use the very advanced functionalities and deep dive in these results. Because as you know, as an analyst, my function is not only to find the problem, but it's actually to understand the root cause of these problems. So through very advanced diagnosis capabilities here, everything from model participation, critical mode shapes, and what if investigations, we can deep dive and understand what are the modes that are the most contributing. How do they operate? Are they in phase or out of phase? Are they driving all in the same sense? And when I'm deep diving into this, now I have understood where the problem is located, what is causing the problem. Now I can work my way into solving this problem. And in order to solve this problem, there is the traditional approach of, I would say, guessing and iterating manually, or we can use numerical optimization. In this case, we're showing an example where we will use numerical optimization to minimize the acceleration levels at the PCB. And so as you see here, the way I will do it, and you can imagine there could be many scenarios out there. We are looking at the fixation strategy or the connection strategy between the PCB and the cabinet. And the technology we are using here is actually a 1D topology optimization targeting the full frequency range. So to the left side of this slide, you see the initial connection points. And with, let's say, a discussion with a designer, we could be adding some new possible fixation locations. This could be discrete location, or they could be a complete space, and we could use different techniques. But out of this analysis setup and optimization setup, the results are very interesting. This is what you see here. The left picture is actually describing the density, the element density of out of this optimization, showing where materials need to be added, meaning where we need to set up a certain connection and design a certain connection. And this describes a new layout. And as an analyst, as a CAE engineer, I am now having the role of proposing a solution to my designer and working with him towards establishing it. At the same time, I am seeing to the right side the potential of implementing such solution that I'm now way below the target. I'm definitely in the safe zone. So again, this is, at a glance, it's a very well established process and workflow that starts from the basics of the vibration analysis, model analysis, to forced excitation in the frequency domain, and the full-blown capabilities with the analysis, diagnosis, and optimization. Number two. So now that we looked at, I would say, on the structural side, what we can do, let's see now how we can transition to the acoustic part and looking at sound pressure levels and environment effects. So the acoustic analysis is nothing strange. We are using, again, the same finite element model, applying the same excitations at the different speakers, but now we are creating what I would call a microphone wall. So basically a series of microphones at a very specific location of interest. And I'm adding this air cavity around the speaker and also in all the gaps of the speaker inside of it. And this is what I would be able to analyze in this case. I'm looking at the sound pressure levels at any location surrounding the speaker. I'm using an infinite element approach in this case. And I can now start deep dive in every aspect of these results. From a 3D control like this one, I can go on a single microphone and look at how the sound pressure level will vary in the frequency range and understand the different effects and the different peaks. And everything I've shown before in terms of diagnosis, relative modal contributions, and frequencies is available for this type of analysis. So again, I want to summarize that this going from the structural model to this acoustic model is just a continuation in the same workflow. And most importantly now, because I can imagine that many of you out there are already thinking, what I've seen here on a one system evaluation, we've done this model analysis, we looked at these loads, we looked at the sound pressure level. How scalable is this? Well, I want to say that this is one of the key capability that Altair offers, is this scalability level. I can very easily go from one speaker model to two speakers, these two speakers into an environment which I'm interested to analyze it, because this is how I'm getting closer to my end consumer and to understand the performance of my product. So in this example here, I'm showing how we can build a room, let's say, where you have your 2.1 speaker system, and we are creating this multiple virtual microphone walls to track the sound pressure levels. And exactly as I showed for one system, we can scale that up and look that for the complete space. We can track how the sound pressure level vary, where we can have some dips, what are the differences at the different location. Anything I'm plotting here is actually all these microphones that I have been setting up. So again, very powerful and very scalable capability from one system to multiple systems. Now I would like to go to the next point. And again, we are in this notion of perceived quality remember what we discussed from the beginning. So what is perceived quality? Why are we talking about buzz, rub, squeak, and rattle? So let us define this and make sure that we are all on the same page. So if you've ever heard about squeak, rattle, rub, and buzz, they are basically unwanted noises that are occurring where multiple parts will come in touch or start rattling or touching each other under certain vibration states. I have these three pictures in the lower part of the slide where you see that under the rattle condition, we are talking about a setup where an initial gap between the parts exists. And these two parts will clap against each other. In the case of squeak and rub, we are going in initial conditions where parts are already touching each other. And now this relative movement will create the stick-slip phenomena between the parts. And depending on the frequency range, we would have squeak or we have rub. And finally, the buzz is actually the displacement of a part by itself at a very specific range of frequency. So we could go into very much technicalities on defining all this, but what's very important is that these phenomena are known in the industry to be the primary causes of lack of perceived quality. And they are not unique to a single industry. You see them appear in all types of transportations, you see them appear in consumer goods, and unfortunately, they are still tackled in an old-fashioned way, meaning with physical testing and quick fixes in the late phases of the product development cycle. So are there any alternatives here? Yes, there are. And this is the process I want to show you here in this second part, where right now we are switching from that frequency domain analysis and going to the transient time domain-based type of analysis. Again, same model will be used. We're setting up, let's say, a scenario where we have a speaker on a table. We have the full capability of modeling the interaction to the table, like the rubber pads, for example. We will be able to track the overall displacement of this speaker. We will apply the excitation as we've seen before at the two membrane. And on top of this, we will be using one of the best practices in the industry for almost a decade now. It's the so-called E-line method. So just to bring some clarity here, the E-line method is actually a methodology based on the analysis of interfaces between parts. And you can imagine that we are creating sensors all over the place, wherever we want to. And these sensors are nothing else than, I would call them virtual accelerometers, meaning local coordinate system definition and spring elements to track the relative displacement between the parts. All this is done on top of this linear finite element model we've been using so far. Now, I've got this question many times before. Well, my products have hundreds of interfaces. We deal with very complex assemblies and packaging situations. I want to say, do not worry. We have very and highly automated processes that allows the user to go through the creation of many of these interfaces, manage them, create all the relevant load cases related to it, all again in the same interface using the same model that is existing. So let us zoom in and see how this process works through this example. You remember our assembly, and now I'm zooming in a location between two components on between the PCBs actually. And what you see here is actually I would be able to track my transient analysis result and the relative displacement between these parts. How do I track that? Automatically, the relative displacement is extracted from this analysis, and the relative displacement is compared to my gap. My design gap or my GD&T. It is also taking into account all the tolerance variations. So we are really entering in a quality perspective. And this is done for all the interfaces that you might have created in your assembly. They could be 10 of them or they could be 100 of them. And from this very high level, I would say visual representation of good and bad, problem and no problem, we can deep dive into the details of these results. And again, an analyst job is about finding the problems, but also understanding the root cause of these problems. This is why we have these high capabilities in terms of model contribution, in terms of understanding how these modes interact with each other and what if scenarios. So in a nutshell, again, what I'm showing you here is very advanced capabilities, but most importantly, all packaged in a very highly automated workflows and processes, which I believe is very important for the execution in a real product development cycle. Now, we've seen how we could identify these different issues, how we can set up this different analysis. Now that we have, let's say that we have identified this rattle, can we consider this rattle in the acoustic analysis? Well, the short answer is yes. We have that process in place again, where from the rattle analysis result, we are able to go back into more of an explicit type of analysis to extract the contact forces at these interfaces, these problematic interfaces. And we can circle back in our linear finite element model to combine both the original loads coming from the speaker, but also the contact rattle loads. And when we have been setting this up, we are now able to compare, and I named them here as a perfect model versus rattling model. What perfect model means is actually a model where the rattle is not considered. Rattling model is where the loads from the rattling are considered. And while it might be a little bit difficult to see the differences in a 3D contour very generic like this, we can deep dive using more of a deep dive in the specific microphone recordings and understand the differences. If this is the sound pressure levels for a perfect model, you see how the sound pressure levels look like for a model where the rattle loads have been included. And now what you can see here, and this is the power of simulation, the blue curve is actually describing the effect and the sound pressure level of the rattle phenomena only. This is something that you can never do in a real physical test, because you can never reproduce a rattle issue without exciting your main structure. So here, this is very powerful because now we are able to see the effect of the rattling and understand, close the gap from the structural analysis to the acoustic analysis. So basically, would we hear this problem? How severe is the problem? So a lot of questions can be answered here. So definitely, again, I insist on this. Capabilities are added and exposed to you, but more importantly, all this is packaged in a workflow and a single platform of simulation. Now, let's put the cherry on the cake. What if we could hear the sound? Well, I want to say the short answer is yes, we can do that. And due to the setup here of a webinar, and you will not be able to hear the sound coming out from my computer, I stepped back to a more simple example, which I think you would be able to relate much easier. If you have two plates that are vibrating and contacting each other, rattling against each other, I think that you would very easily imagine the clicking sound, the repeating clicking sound during a certain period of time. Well, what you see here is actually the output of the relative displacement of these parts. And here you see the acoustic results, basically my pressures, magnitude, and phase. So what I'm able to do here is actually pick these results from the acoustic analysis and plug them into a post-processing capability in our mathematical tool based on Compose, where we can actually generate the sound pressure level versus time and generate a wave file and listen to it. So what we are creating here is really trying to close that gap of subjectivity, right? Will this rattle occur? How severe it could be? I can analyze it and see if it's worth to be investigated. And if it's worth to be investigated, can I listen to it and see how severe it could be? So I want to say in a nutshell, what we are talking about is about enhancing the simulation process. adding more capabilities and focusing on workflows. So as you see, going from the rattle analysis to the acoustic analysis, but we are adding that last step, which is actually generating and listening to that sound output. To conclude from my side here, I just want to go back to where we started. We took this system, a speaker. As you see, it's probably not the most complex of the smart speakers out there in the market, but we took certain challenges and requirements, very few of them, and we could see already how these challenges means multi-physics and multi-attribute and multiple solvers to be considered, a quite complex matrix and a quite, I want to say, the need of quite advanced capabilities. But once again, and I think Altair key aspect here is to propose capabilities, but not only the capabilities. It is very important to propose them in the context of a process and a workflow that allows them to be incorporated in an existing product development cycle to match the times or be even faster. With this, I'm happy to take any questions out there.
Great, thanks a lot, Ismail. One last question that we have here is, so in your presentation, what were you using for acoustic simulation?
So for the acoustic simulation, we are using our solver, OptiStruct. And I can mention that in terms of capabilities, we can cover the different needs of the low frequency or the high frequency. For the low frequency, we are using the finite element approach and the infinite element approach with OptiStruct. If there are needs for the much higher frequency, as we see in other problems, we can use our solver SEAM, which is based on statistical evaluation, statistical energy approach.
Great. That's all I have from my end,